Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on the YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
Oh shoot, I didn't click it in time.
No, I think you're.
I didn't do
it's
it.
Okay.
It was so
Maybe.
sloppy. I was thinking about stashing equipment away so that our colleagues can't steal it. Because there's a problem in our office. I'm letting you behind the curtain now. That we have equipment and our colleagues steal it. And they're doing experiments with it and they're testing things, which is, in theory good, but it's ours.
Yeah. This is no different than like you schedule to use your instrument to do an experiment, but someone else takes it.
Yeah, did you ever have that in the lab? I didn't have. We usually, when I was starting graduate school, we had like a couple of potentials, a couple of setups or whatever it was, and I would usually show up at like early in the morning because I'm a weirdo, and no one else showed up for like 5 more hours. So I got to get I didn't have to like sign up for a time or take the equipment, but that is what that is, right? It's like, this is mine, or at the very least, it's mine for these hours. And someone just doesn't care. And they're like, no, this is mine now. I'm going to take it. Like our boss will take it and just test with it for, oh, he only needs it for 7 months. No big deal. We don't, and we don't even know it's gone. It's frustrating. It's frustrating. Stuff just walks away.
Yeah.
When you least expect it. And then when you need it, it's not there.
I know. It's the
no
worst.
respect.
No respect.
Welcome, everybody.
Yes. Welcome to another episode of Ask Us Anything about electrochemistry. We got a bunch of questions. Yeah, we have a few questions.
Let's get right to it. I want to get to these that this is a hard name. I can't tell, is this Biahuos is nice, or is this like Biahuo is nice?
Yeah.
Or is it like just a long name that's a little tricky to pronounce?
Yeah.
I'm not sure. But in any case, this person asked a question 30 or so minutes ago, so they're chronologically first. And so there's two parts here. The first is when you apply voltage to a supercapacitor, each electrode reaches a certain potential. How is that? And how to know these potentials using a potentiostat, because we only know the E working, basically. So there's two possibilities of an answer. Both are relatively simple, I suppose, and they're just related to how a potentiostat functions. So the first answer is that if you are doing a supercapacitor experiment and it's 2 electrode, which is, I think sometimes you use like a reference electrode if you're doing a 3 electrode testing a material for a supercapacitor. But in some cases, it's just a 2 electrode system. And so the answer is minus EWE. That's simply it. So with a 2 electrode system, the working and counter electrodes are equal and opposite by definition. This is just how it works, right? If it's a 3 electrode system in the second case, you do not know the potential at the other electrode, only the working electrode, because you have a reference. And so if you have, for example, a bipotentiostat, or you could probably use like a multimeter, whatever, but basically if you are interested in also passively measuring the potential of the counter electrode, so to speak, or the other electrode, whatever you want to call it, in your device, and you have a reference electrode, you would need a second voltage measurement pathway, which would be, again, like an external multimeter, a second potentiostat operating passively, a bipotentiostat where you can use the second working electrode sense lead. And you would basically measure the voltage between the reference and the counter separately. And you could then measure what the potential is. And it will not likely be exactly equal and opposite to the working electrode because of the presence of your reference. So those are the two possibilities for what the other quote unquote potential is in a system, whether it's a two or three electrode system. And this isn't specific to supercapacitors. This is a general kind of a phenomenon with a potentiostat and a 2 or 3 electrode system. So if you have a specific question about a supercapacitor, or perhaps you needed some more clarification on that related to that field, right? I've kind of answered it irrespective of the supercapacitor. This could be anything. Please let us know. And then the second question was, in addition to a nice comment thanking us for the live stream, I appreciate that. I did mention that I'm just not flexing by posting it here, but I did see your I appreciate your comment very much. And the second question was how to choose the best equivalent circuit for fitting impedance. I know it depends on your material, but how can you predict the phenomenon you have in your material? This is a good question because the answer to the first part of your question is the second part of your question, which is that it depends on the material, not more than just the material, the system, more broadly speaking. But the last part of your question is actually the best part of it, which is how can you predict the phenomena? And that's the thing that I actually feel like I say very often when I'm talking about circuit fitting and, I've used the phrasing like, picking the circuit is your job because you have to know something about your system and you have to know what's going on. And so your question is sort of about that. How do you predict those phenomena? That's also kind of a hard question to answer. Obviously, it depends on, what system and material you're studying. But a lot of times it's by looking in the literature as a sort of a cheat way to do it, right? Find someone else who has studied that electrode in this electrolyte and what processes that they report. Another is by other kinds of electrochemistry experiments. So for instance, if you do cyclic voltammetry and you get some peaks, that indicates a Faradaic process, an electrochemical process, a redox process, which in the terminology of impedance would be like a charge transfer process, which would make like a semicircle. And so the number of peaks and the potential you pick for your impedance experiment may dictate what you would expect to see. So, if you get one semicircle and you're at a potential around a peak from the cyclic voltammetry, well, that's one example where I'd say, okay, this is a charge transfer process. That's my redox process. It's the oxidation or the reduction, depending on the potential and all those parameters. And you have a double layer, electrical double layer. And so the semicircle comes as a result of essentially the time constant, the combination of your charge transfer resistance for that process, as well as the electrical double layer. And so that's just sort of talking through this question, which is again, what are these phenomena? How do you predict what will happen? And then ohmic resistance, uncompensated resistance. Well, you can predict that based on the electrolyte you have. Is it non-aqueous? It'll have a high R0 or leading resistor. Is it aqueous with high electrolyte concentration? It'll probably have a very small R0. Is it a battery? It'll probably have almost no R0 or milliohms of it, very, very small amount. It's very tightly packed together. So there's a lot of different possibilities there. And then, of course, things like diffusion. Are you likely to have, a semi-infinite plane diffusion? Do you have a situation where you are doing a Faraday process and then there's a lot of, a dilute amount of reagent that's diffusing to the surface? You have a thick diffusion layer. Are you rotating? Do you have a fixed diffusion layer? These are all just things I'm talking through some of the different phenomena that translate to the results. And a lot of times you know some of the things that I just mentioned, and then you look at your impedance results and hopefully they mirror those things. Sometimes they don't. Sometimes it kind of goes the other way, which is that you see, well, I should have a charge transfer process and some diffusion, but all I see is a semicircle. I don't really see diffusion. And so then you're sort of left doing the other thing, which is based on my impedance results, how can I infer what's happening? You can do both directions in some way, right? You can say, I kind of know what's happening because at this potential, I have this process. And so that should give me this impedance result. And sometimes you get the impedance result and you say, well, I thought this would happen, but this is what my results tell me. And so as we say, as scientists and engineers, theory guides experiment decides. What is it?
Yeah, that's it.
I'm butchering it.
Yeah,
is that right?
Theory guides, experiment decides.
There, I did say it right.
Yeah,
okay, I don't know why I was doubting myself, but yeah. So your experiment your theory is I have 12 charge transfer processes and 9 modes of diffusion. And then my experiment tells me I have 1 charge transfer process and 1 bit of diffusion. And you're like, okay, well, that's the answer, right? So I'm being silly. That's kind of a ridiculous thing to say. But the data you get can also inform those phenomena that you hypothesized were happening. So I hope that kind of talks through those problems a little bit for you, and just, kind of gives somewhat of an overview, I suppose I'd say, of those of your question. If you have a follow-up, please let us know.
Yeah, that reminds me of something you said a while ago, which was that there was a case where someone was doing impedance on their system, and their impedance data kept changing, and they were like, "Well, nothing's happening on my system. Why is my impedance data changing?" And you said, "No, like your system is changing.
Yeah.
Like just like one thing has to inform the other.
Yes.
Like if there's a weird feature in your EIS, it like it didn't come out of nowhere. It's absolutely related to
I've
your
never thought of
system.
it that way, but I guess that is exactly right. That's a direct illustration of the theory guides experiment decides, because the theory is that I haven't changed anything, and the experiment says you may not have, but something changed. And that's the other thing that I feel like I say that a lot to people. I try to say it in a nice way. I always feel like it sounds like a mean thing to say, but it's just true. And I'm trying, I don't want to, I don't know, sugarcoat it sometimes, where people, customers will say this a lot, or just, in scientific discussions with people, it's like, oh, I did 2 experiments. I did one last Tuesday and I did one today. And it's like, I didn't change anything. It's exactly the same. My results are different. And my response is usually like, it's not exactly the same. But I did this and this and this. And something was different. I don't know what, but something was different. The surface condition of your electrode was slightly different. It was not polished exactly the same way. The counter electrode wasn't touching the solution exactly. The surface area was slightly, there was the reference. I don't know. Something was, this is electrochemistry. It's terrible and no one should do it. It's terrible. It's very common for this to be the case. So, that's why we collect the data, and we do our best to get consistency, but it's an uphill battle for sure.
We have a question from Mustshake. Mustshake is asking, what's the difference between reversible, irreversible, and quasi-reversible cyclic voltammetry? So this is a very good question. Interestingly enough, there's a fairly simple answer. To demonstrate this, or to kind of walk through it, I'm going to share my screen. This is, you've probably seen us talk about this times. This is Aftermath Live. It's our simulation software. So I'll actually be simulating cyclic voltammograms under those conditions, just very quickly. So I'm going to just start with a very simple 1 electron transfer reaction. And so in this case, what I want you to focus on is this kind of middle part here. This is the this is really the difference between a reversible, irreversible, and quote quasi-reversible reaction. So let's just do a very basic one. We're going to simulate. This is the regular cyclic voltammogram that you see. This is for the completely reversible reaction, which conceptually just means that when A plus an electron goes to B, B can go back to and oxidize to form A and an electron. That's all that means. And this is what the cyclic voltammogram would look like. If, for example, we had an irreversible reaction, it means that A plus an electron just goes to B, and B cannot go backwards. And when we simulate this, the voltammogram looks very different. Now, notice one thing to keep in mind is that the current axis, it changed a little bit. This is the same amount of current as before, but you'll notice there is nothing coming back. There is no oxidation process. We only reduced A to B, but B didn't go back and convert to A. And so something very simple, like a physical example, is whenever you evolve a gas, for example. So if you're reducing like hydrogen, your protons to hydrogen, the hydrogen gas floats away, and then it can't go back. It can't go back to being H plus and oxidizing. Only when you have something like adsorbed hydrogen could that happen, and that's when the mechanism becomes the thing in question. Now, the other thing that you mentioned, let's just go back to this guy here. So now the other thing you mentioned was quasi-reversible. And I know some people, they have mixed feelings, I would say, about quasi-reversibility. Quasi-reversibility for a single electron transfer process simply has to do with this thing right here, the heterogeneous rate constant K. When you have quasi-reversibility, it means that this rate constant becomes low. So as I increase, or if I decrease it, you'll notice that I start to get some peak separation. I'll make this bigger so it's easier to see. You start to get some peak separation. It's not very obvious at first, but as I make the rate constant slower, the reversibility of the system becomes less and less. Right. And so when we talk about quasi-reversible reactions, what we're really talking about is when the heterogeneous rate constant for a single electron transfer reaction starts to get slower and slower and slower. Another thing that sometimes gets coded into this is when you add a chemical step. So if you have an electron transfer process coupled with a chemical step, and I'll just, again, kind of fill these in. This is what we might see, normal. And this is a reaction where you have A plus an electron goes to B, but then B is in equilibrium with C, some other chemical reagent that doesn't have anything to do with A. And so quasi-reversibility can also be observed when you adjust the rate constant here. So let's say you make this several times faster. You'll start to observe like, oh, maybe this is a quasi-reversible reaction or something like that. And actually, if you do, say, a combination of these things, you also get more kind of weird quasi-reversibility. And the chemical step also plays a role, but you have to be careful. But fundamentally, I think when it comes to electron transfer, single electron transfer, not coupled to any chemical reactions, the notion of reversibility and quasi-reversibility has to do with this rate constant. But in the event that it is just A plus an electron goes to B, it is a different thing, and that is quote irreversible. You can actually make the rate constant very, very like fast, or make it so much in one direction than the other, but you still won't get a voltammogram that's truly irreversible. Mass transport and other things just start to play a role. And if you want to learn more about this, I would actually encourage you to play around with Aftermath Live, just even for a month. You can even play around with other features and stuff like double layer capacitance and uncompensated resistance to understand how does the voltammogram change as you start to adjust these parameters. It also just helps you learn electrochemistry a lot more. So that hopefully answers your question. I don't know if you had any other comments. Doesn't look like you had any other comments on that. So yeah, there you have it, Must Shake.
All right. There was another set of questions from Apurva.
Mm-hmm.
So she says, while studying overall electrolysis that is performing water splitting in 2 electrode electrolyzers setup, counter and reference electrodes are connected and act as a cathode. As there will be no concept of reference electrode here, how the potential should be swept versus reference electrode potential or OCV or any other option if you have in your potentiostat. So first of all, I think that you're making a mistake. The cathode usually connects to the working electrode. You can connect it any way you want, but you'll just get a different polarity of your voltage. So for instance, if you have a water electrolysis system, usually, really, if you have any sort of fuel cell or electrolyzer, the cathode connects to the working electrode and the anode is on the counter in the reference. Now to the last part of your question, this isn't something that like my company has or does for a good reason. I won't maybe get heavy into this discussion, but some software programs and potentiostat companies have an option in their software for you to specify what voltage to apply and versus what reference. I don't particularly agree with this choice, simply because you're telling the potentiostat what potential to put. The potentiostat doesn't need to know what your reference is. It just needs to know what a potential to apply. So when you tell it to apply 250 millivolts, and then you also tell it to apply versus do that versus silver chloride or something, you're just telling it to apply whatever 400 something, because it's going to just do the math for. It's like that's your job. It's not the potentiostat's job to do that fundamentally. I kind of just sort of generally disagree with that. So the first thing I'd say is that in your potentiostat, if your software has the ability to like make you pick what the reference is or something, I don't know that that's wise. Okay. So as much as possible, you want what would you just be called an absolute or a reference potential selection. So for example, when you say set working electrode to, whatever volts, it's just versus the reference line, which in your case is connected to an electrode. So there's that. Now, doing voltage versus OCP is also an option. If you measure OCP or OCV first, then you can do, for example, a sweep versus OCV. Now, I'm trying to think here. This is an electrolysis cell. So let me pull up something just as a I have a slide with an electrolyzer thing in it. I want to pull it up. Might help kind of illustrate things and also work out the point of this here. So proton exchange electrolyzer. So this is an electrolyzer. I'm just sharing this screen. Sorry, give me a moment. I'm getting there.
Mm-hmm.
This one. So this is an electrolyzer. This is like a proton exchange electrolyzer. And this, I'm just sort of assuming this is what you, what are doing here. So let me think here. I'm just thinking out loud. So maybe you are correct. I'm rethinking this. If you put the working electrode on the anode and the counter electrode on the cathode, this here is an oxidation. I don't think it matters. It's just going to be what it'll be, either positive 1 volt or negative 1 volt. But ultimately, with the electrolyzer, you have to provide the energy for it. So for a fuel cell, so let me draw. Where's my drawing? Okay. The potential of this side of the cathode reaction is 0, right? This is the potential of this as a reduction. This side here, you can see that this is written as an oxidation reaction, but the E0 here is 1.2, 1.23 or whatever. But that's written as a reduction. That's what it is. Okay. So basically, this is like the opposite of a fuel cell. So the reality is that the E cell of an electrolyzer is minus 1.23 volts, which means that it's not spontaneous. You have to provide energy. Okay. Now with a fuel cell, what you have, for example, is I should do a fresh slide. There's like there's too much stuff around here. I can't see anything. All right. So with a fuel cell, for instance, your open circuit is 1.2 volts, and you have current here. This is voltage. You're not. It's just voltage. This is sort of a distinction that I like to make in my mind. I don't know if it's like everybody exactly looks at it this way, but it's sort of like people like to use the word potential. When I consider things like you're talking about with an electrolyzer or a fuel cell, it's 2 electrodes, and I consider the word voltage to be like more appropriate, so to speak, because it's just between 2 electrodes. And to that point, because your anode or cathode are connected to both to the reference and the counter electrode, whichever order it is, you don't have a proper reference. You just have the voltage. So it's just the energy difference between the two. What that means is that the exact potentials of the anode or the cathode are unknown, but you just know the energy difference between the two. So with a fuel cell, we do something like this, which is that we drop the voltage. What that means is that we are, do I have the fuel cell one? I have the fuel cell one. So when we do a fuel cell here, this is the working electrode on the cathode side. This is the counter and the reference on that side. And so we have the E cell, the voltage of the cell, the potential of the cell, is E cathode minus E anode, which is 1.23 minus 0. So it's positive 1.23 volts. That's the theoretical potential of this. This is 1.23 and this is 0 volts, right? And so what we do when we drop the voltage here, the voltage of the cell goes down. So if the voltage of the cell is 1.23, well, what is the voltage here and what is the voltage here? We don't know. That's the point. But let's just give one option, right? This, if I drop the voltage, this could be 1 volt, and this could be 0.2, and so then my E cell at any moment in time is 0.8, right? Well, what does that mean? Well, my E at my cathode is less than 1.23, which means it's driving the reduction reaction, which is what I want to do. That's the oxygen reduction reaction. At the anode, it's greater, so it's driving the oxidation, which is this reaction producing protons and electrons. So that's what we're doing. Now, reverse those concepts for the electrolyzer, right? I want to drive the reduction at the of the hydrogen reaction now and the oxidation of the anode. And so what it just means in short is that my voltage will be exactly opposite. So basically what you're doing is when you connect your leads, I think if you connect the anode to the working electrode and the cathode to the reference, you'll get a negative voltage. So hopefully you have a negative voltage. I think that's correct if that's what is the case. So it's almost like the opposite here. Your voltage axis, your OCV will be roughly minus 1.2. Now the sweeping is that okay. I should clarify. I don't 100% have the same experience with electrolyzers as I do with fuel cell. This is like fuel cell here, right? With an electrolyzer, but it's a similar phenomenon, right? So E cathode minus E anode in the case of an electrolyzer is 0 minus 1.2. So I have minus 1.2 volts of my cell. So if I instead make it more positive, so if I have minus 1 volts, similar kind of a phenomena, right? How do I get minus 1? Well, I could have 0.2 minus, I should do 0.8 again, minus 0.8. 0.2 minus 1.0, right? Equals minus 0.8. So if my E cell is minus 0.8 for my electrolyzer, right? What does that mean? Well, it means I have a voltage at the, I have to reverse my nomenclature here, at the anode of minus 1, which means it's higher, which means it's driving the oxidation, this is what I'm trying to do. I'm trying to produce oxygen. And then at the cathode, I am also higher, so I'm driving, wait, do I have this backwards? Sorry, I'm getting myself twisted up here because I'm usually thinking in terms of a fuel cell. All right, let me back up from this discussion because I'm getting myself twisted on the nomenclature. For I usually think in terms of a fuel cell. Electrolyzers kind of mixing things up. Let me say this: the sweep that you're going to do is a straight voltage sweep from whatever the OCP is usually close to 0. So that's how it works in a fuel cell. I'm thinking that's how it works in an electrolyzer. Because as you change the voltage, what you're doing is you're driving the reactions at both electrodes. You aren't going to know, for instance, let me just stop sharing and just talk the rest of this way. And apologies for the mix up. The electrolyzer, I'd have to, rather than working it all out here live with you, I'm going to quit while I'm ahead, because I think I'm trying to get the numbers right. I've done fuel cells, and those numbers are easier for me to do, and I'm inverting them and mixing it up. So as you adjust the voltage, there's 2 ways of doing that. One of them is with a linear sweep. The other is with a bunch of chronoamperometry steps. So as far as that's concerned, you have like minus 1.2 volts as your open circuit. Then you're going to just apply minus 1.1, then minus 1, then minus 0.9, then minus 0.8. You're going to step the voltage change a little at a time. Again, you can either do that with a linear sweep at like really slow scan rate, like 1 millivolt per second to like 5 millivolts per second, or you can just apply a bunch of voltages one at a time, like chronoamperometry, and see what your current is there, and that's the amount of current that's driving, those water electrolysis reactions at each electrode. Okay, so it's not volts versus ref or anything like that. Like the nomenclature, it's just the voltage. So like the nomenclature for a fuel cell or an electrolyzer isn't the same necessarily for a full cell. The way you're describing it is not the same as with a 3 electrode system. Like should this be versus silver chloride or versus hydrogen, whatever. It's just the voltage of the cell, because it's just cathode minus anode, basically. So hopefully that kind of gets into that for you. And sorry for the little bit of a mix up with the numbers of the voltage there, but the voltage of a cell, again, is just the difference between the two. So it's not versus a reference in that case. There's no reference electrode present.
Okay. So the next question from Ahmed, and Ahmed says thank you for replying to his questions in advance. And he's saying, I'm working with the development of electrolytes for, I think it's the lithium metal batteries, or I've even seen liquid metal batteries, but they're batteries. Can you please explain how to interpret sequence test to measure transport number via EIS, followed by I versus T measurements, then EIS again? I have not worked with measuring the transport number of anything, so I don't actually know how it's calculated.
This brought up a memory for me about something I had done. I don't know if it's the same. If there's transference number, is transport number the same as transference number?
I looked at the. Oh, it's also, yeah. So it is called the transference number as well. And
so I had. This has definitely been. I answered this in one of our. Let me see if I can find it quickly, but there's what's called the Bruce Vincent method. So here's a paper. I'm gonna share my screen in a paper here. I had this isn't something that I know very well, to be full disclosure here, but we had a question about this a long time ago, and I looked into it a little, and I believe I gave a pretty concise explanation of this method to measure the transference number, which again I think is the same as transport number, and it's by 2 researchers from, I guess this is the 1980s, I think. So Colin Vincent and Peter Bruce. So it's called the Bruce Vincent method. And there's another paper I think I have, and I it's somewhere on my computer. I don't know exactly which one, but I think this is what you're referring to. It involves time transients, and there it's this one, I think. I'm trying to remember. Again, what I'll do is find. If you want to move on, is that the last question by him? I will try to find where I answered that before, and I'll try to link that episode, because I think that my explanation exists in one of our earlier ask us anything about electrochemistry live streams. I remember that I talked about this, and it's not something I
Mhm.
have done personally, so I need to like remind myself
Yeah.
what exactly how it works. But at least what I can do is hopefully I'm going to find the episode and I'll try to link it for you. That's what I'm going to try to do now. If you want to
Okay.
move to the next question.
All right. So the next question is from Mohammed, and we do have a lot of questions. We know where we are trying to get through them, hopefully relatively quickly. How to calculate conductivity of hydrogel if we have only impedance data? Please explain which one is considered the conductivity. I think so. Generally, it would just be the inverse. Like, well, I guess I would need your help on this one, Neil, because I would imagine you would take the real impedance value of whatever your Nyquist plot is and the impedance data and take 1 over that in order to determine what the conductivity is based on the impedance data.
Yeah.
There's an inverse relationship between conductivity and impedance. And
yeah, this is a thing that also is like, it drives me nuts because I feel like it's hard to get
a straight
a
answer.
straight consensus in terms of the literature. But basically, you have something like the impedance. The impedance or the resistance that you get R, and so the conductivity or the conductance, and I always mix those two up to be honest, is L over RA. This is the sort of common form because this is typically units of Siemens per centimeter, basically. And so there's this length unit involved because L is centimeters, right? And area is centimeters squared. So it's like you get centimeters in the denominator, and 1 over ohms is Siemens. So this is kind of the formula that's used. And so the question is, this R, what is it, right? And so I think it's what you said, right? You would typically take the Z real of what?
Yeah, of that data point at that frequency.
Exactly. And so it's you're drawing some conclusions.
Yeah.
At that Z real at that frequency is the resistance associated with the conductivity of your material, which may or may not be accurate. I mean, there's open questions there. Hopefully what you're trying to do is you want to find a Z real where minus Zi is, roughly 0 or close to 0, because then Z real is roughly equivalent to Z magnitude. And there's no imaginary component. That's about as much of, I guess.
Yeah, because there's no I mean, I was gonna say there's no imaginary conductance, sort of say.
There is in this head.
Yeah.
I imagine conductance. No, that is the formula that's used for conductivity. Yeah, there's this is why a lot of folks as well, they do DC methods where they just do like a LP. It's called LPR, but I mean basically you just do a slow sweep over a very narrow voltage range, and it makes a straight line. You have I versus E, and the slope of I versus E by Ohm's law is R. That's another way to get the R to get an estimate of that. But yeah, you can typically just get a relatively fast frequency scan where it's mostly just Z real. Zi is pretty small, and then you can do something like that.
Yeah.
That is kind of the way to do it. And then I wanted to follow up here. I did post in the YouTube chat here. This is the timestamp from, I think, episode 26, where someone asked about the Bruce and Vincent method, and I talked about it. I have memory of myself talking about it, but not exactly what I talked about. But I do know that I figured it out. Someone had asked it probably midweek, or I gave myself a week to answer it, and whatever it was, I did some research and looked into it. And again, it's like, there's a that you have to like fit a transient, like a decay curve. And there's another paper that I can't find at the moment. I have to locate it. But I believe this is what the transference number, what to do basically. Which was this Ahmed's question? No, yes, yeah, Ahmed's question, because it involves EIS I versus T. There's a I versus T, like a chronoamperometry decay curve, and there's an impedance aspect to it. And so please check that out, Ahmed. I believe that may answer your question. going through that method. That's my hope that is. And if you see that and that isn't it, please, let me know, and I can again sort of try to look into it. It might take me sometimes we shelf the question, I answer it in a week when I've had time to really give a better answer. We just do the best we can here live. So
yeah. Aporva has another question. Is it necessary to calculate collection efficiency every time calculate the Faradaic efficiency, or can we use the value which we get from the Pine website for a specific RRDE that we use?
You can never trust Pine.
Oh, I hope you trust Pine.
I'm just kidding.
My general thought is like, you don't have to calculate the collection efficiency every single time because it's a value based on the geometry of the RRDE. What I usually recommend is that you determine the Faradaic efficiency empirically. So do a collection efficiency experiment where you either oxidize or reduce a well-characterized redox system in solution. Just kind of get like a nice perfect RDE, RRDE type of thing, and determine experimentally what that collection efficiency is. So for example, if you had, say, ruthenium hexamine is a very good, well-behaved redox system. In an aqueous system, apply a, sweep the potential negatively on your disc electrode, and then hold the ring at a positive potential. And, you'll get I'll just kind of draw out roughly what I'm talking about. But roughly speaking, you're going to just get what I would consider to be a quote typical RDE. But let's say you're reducing ruthenium hexamine, and we'll use the Pine colors of red for the disc electrode, the working electrode. And so you would get something that looks like this. And then you have your ring, which would be something that would actually be at the same current. It's 0 at first, and then it would kind of go out like this. And you would just measure, whatever, this is here. It's a 1 electron transfer reaction. So you have your both of your currents, the difference. So this is your I disc, and then you have your I ring, and then you would just take the ratio of those two for a perfect system. So we would call this like a perfect system, because when you have like because it's based on the geometry of the disc and the ring, you may have things like coplanarity issues. Like even if it's a little bit, there may be subtle differences in the geometry of the ring, subtle differences. What is a perfect circle? Can anyone machine a perfect circle? I don't know. But all I'm saying is that when you have this value that's determined empirically, which is IR ring current versus I. Actually, I'll use the lowercase so that's not confused with. Actually, it'll still be confused with IR drop, but and let's say it's 20%. Yes, once you get this value for your particular RRDE, then you can use this every single time. Basically, until first off, it should be very close to the theoretical amount. Ideally, it won't be exactly, but it should generally be close. But then after that, like, hey, it's 20% every time you do an experiment, you would compare it to this 20% for calculation of the Faradaic efficiency. Of course, if every time you do an experiment, and you can also do something where if you have been determining the collection efficiency every single time you do an RRDE experiment, and you notice that it's deviating like crazy, you have another issue, that might be happening. But ideally, it should not be changing. Okay. Moving on, Ahmed has another question, which is, and we do know that there's a ton of questions. We are getting through them.
We're getting there.
Slowly but surely. He's asking, can you explain what's the physical meaning behind increasing discharge capacity of LiNCM coin cells after the first activation cycles when transferring from 0.1 to 0.5 C rate.
Increasing discharge capacity.
Oh, what's physically happening? Like, because
transferring
increasing the C rate's just making the
you're scanning faster. Why would your discharge capacity go up?
Increasing discharge capacity behind increasing discharge.
So,
like the fact that it's just discharging faster.
No, increasing
No?
discharge capacity means it's giving you more energy,
Mm.
and that shouldn't happen when you increase your charge rate. What is the physical meaning behind increasing the discharge capacity after the first activation cycles when transferring from 0.1 to 0.5 C? I think I don't understand why that would happen. Is there no clarification here?
I don't think
if you're going from 0.1 C or C over 10 to C over 2, you're charging or discharging faster.
Mhm.
Your performance should be worse almost all the time. So if you're getting better performance, increasing discharge capacity after the first activation cycles, my only guess is that you have some kind of process that you don't want to be happening, which is that at a faster rate, you are either encountering secondary SEI storage, or you are unfortunately ripping apart your electrolyte, which is leading to the appearance of improved capacity. Everything about this feels backwards. So to me, it's kind of a red flag. The capacity generally will be worse at faster C rates and better at slower C rates. So if you're experiencing the opposite, it usually means there's something kind of unfortunate happening, like what I talked about. Like secondary SEI storage can sometimes contribute to improved capacity, which it's a phenomenon. It's not the end of the world. But when you get a breakdown of the SEI, you can start having a lot of current cause or a lot of it looks like it's giving you more capacity. It looks like it's performing better, but it's actually just ripping electrolyte apart, and it's damaging. It could be forming dendrites. It could be doing other things that are not desirable. So physically, I unless I'm misunderstanding your question, or you wrote it, you mean, decrease instead of increase, or something. I'm misinterpreting your question. If I'm understanding it correctly, to me, this is a red flag, and something is going wrong with your battery physically. And so that might be something to look into, I believe.
Okay. Banam has it seems like a very long
it's a G question.
It's also not an electrochemistry question. It's just a general chemistry trying to balance a reaction with the stoichiometry, not necessarily of like the stoichiometric coefficient. It's just like the coefficient of just like, well, how many atoms are connected to this one atom or something, like like SOX instead of SO2 or SO3 or something like that. There's no ions. So it would be a bit much for us to kind of go through this considering the questions we have. It's also not an electrochemistry question.
Yeah. And to be clear, this live stream is intended to be a forum for discussing some research, electrochemistry, obviously, specifically research kinds of questions, and some of these questions that are like just clearly taken from a test. Like you're probably an undergraduate or a graduate student, and you have an exam or a homework problem to work on, and that's not precisely the point of what we're trying to do here. So we will politely pass on this question, I believe, and move on.
Yeah, it looks fun.
I remember doing
I'd like to
stoichiometry.
go through this, but it would just take way too long to kind of.
It's not
go through it.
It's not exactly the point of this this forum, unfortunately. I think it's not to walk through, that's what, your TA or your professor or office hours in your university, in your class, wherever this question came from, that's really where those specific things are more appropriate, I suppose. So I think Anton is the next question.
Yeah, Anton is the next question. Are the typical Nyquist plots found in textbooks mostly related to systems with redox species dissolved in solution? How and why do these typical Nyquist plot shapes change when using electrode modified? Is there another part? Just, I guess, modified electrodes?
I don't think
or
there's any
electrodes
other part.
mode.
So I guess it's modified electrodes, I suppose.
I think so. Anton, if you're listening, just clarify.
So yes, I think they are mostly redox species dissolved in solution. That's probably most common. Whatever you're trying to oxidize or reduce is some ion or some species in solution. I think that's probably accurate. How and why do these typical Nyquist plot shapes change when using? I guess it almost looks like modified with. Were you asking if they're modified with something?
It's almost like very important that we know what the rest.
Yeah, modified with what? Because if you're asking if you modify the electrodes, will the Nyquist plots change? It's like most probably they will.
Yeah.
But how and why depends on how you're modifying the electrode.
Yeah.
And even then, if you ask specifically how it's modified, I mean, we can try to, if I have knowledge of that specific kind of electrode modification and what it would do and why, I would try to answer that. But again, this might boil down to something that's sort of extremely specific. Like if I modify my electrode with a thiol group, how and why will the Nyquist plot change? It's like, I don't know, specifically that exact example. I can draw some infer, but I don't.
Yeah, well,
that's just an example.
That's an example.
Yeah, just as a random thing that popped in my head. I mean, it's not.
But if you had like a porous, if you modified your electrode with like a porous membrane, it would look different. You'd have a different type of shape.
That's a good example. Yeah, if you have a porous sort of structure, you might have a fixed diffusional path length, through a pore. You might have like the Nyquist plot might change from a Warburg infinite to a Warburg short, for example. That could be one way that changes. So there's certainly ways that you can get around rationalizing those things, but I think it would be, as we said, trying to get a specific answer to how you're intending the modification, or what's on your mind in that regard. I think there's a lot of ways to sort of take that that question.
The next question.
Good luck pronouncing this.
Yeah, I can't pronounce it. I'm gonna call you AA.
Yes, if that's even an A.
If that's an A,
it's Russian or Ukrainian or one of these Eastern
acrylic language. What is it?
Cyrillic alphabet.
Cyrillic alphabet.
We are not very well adept at reading this alphabet, unfortunately.
Sorry. But he says, what are the types of circuits for EIS analysis, and what do they usually represent? How should I start analysis of an Nyquist plot? We have a one of your slides in the beginning of your EIS webinar has a list of all the circuit elements.
That's a good point.
We can just go through that relatively quickly.
Yeah.
I think I might have that for the EIS Rutgers talk I gave. If you want me to pull that up.
I have it here.
Okay.
This one. So this slide has all the circuit elements. So let me share my slide here. Types of circuits. So the types of circuits, this is a sort of quick summary. It's not exhaustive necessarily, but it's a quick summary of the symbols, circuit elements that are used. So we have resistors right here, and typically this represents an electron transfer across an interface. So this is like a Faradaic process. So a resistor exists as a representation of charge transfer process, kinetics, often a redox process. A plus an electron goes to B. The resistor is usually an indication of how difficult it is to move that electron. Capacitor is the next one, and that typically represents electrical double layer Non-Faradaic processes, like if a supercapacitor, it's charge buildup at an interface. So that's what a capacitor is used. Inductors are not used too often. A lot of times you'll have inductance as a result of cell cable kinds of effects, and sometimes you get these weird inductive effects at low frequency, which we're not going to talk about. But it's often not as needed and not as represented in most impedance data. But it is a sort of fundamental electrical circuit, I guess. It's a different way of storing charge than a capacitor. And basically, we use capacitors because effectively the way charge is stored mainly in an electrochemical system is through capacitors, capacitance, basically. So capacitors are used far more often than inductors. Then we have constant phase element, which is a CPE or a Q. This is a non-ideal capacitor. So the reality is that capacitors do not actually behave perfectly like capacitors or in an electrochemical system for a variety of reasons. And so we use a kind of engineering tool called the constant phase element to represent that non-ideality. And then we have some special elements, and I'll just show two of them here in this chart, one of them being a Warburg element. The Warburg element describes the impedance of diffusional processes. And so that's, species moving towards or away from an electrode surface, mass transport. And so we have different Warburg elements to represent that, both infinite and finite, where the effectively the diffusion layer thickness is either infinite or semi-infinite and growing, or finite and fixed, as in the case of like a porous membrane of some kind. And then a Gerischer element is sometimes used when we have a system that includes a chemical and an electrochemical reaction coupled together. And so we have a K in the mathematics of a Gerischer that is the first order irreversible rate constant. And then you sort of asked like how they look on the Nyquist plot. I mean, there's a lot to that. In fact, these slides come from my impedance webinar. I would encourage you to check out our webinars playlist on our YouTube channel. That I go through a lot of these. There's a lot that can be said about what the Nyquist plot looks like for what the circuit is. And so this is like two charge transfer processes, RCs. You'll get two semicircles. And so there's a lot that I can go into that I won't necessarily drag on right now about as far as those are the list of the circuits and then how they combine. For example, resistor and capacitor in parallel like this gives you a semicircle on the Nyquist plot, gives you a peak on the Bode plot. There's a lot of things that can be said about the combinations of those circuit elements that I just listed, and what they look like on a Nyquist plot. And that's probably something that is better handled, and it's a lot more to be said about it. So that's why I have webinars on that.
So Anton did get back to us with what he meant. I don't know if we wanted to
we could try
to just
it looks
get
like
to
he's
his
saying
question.
metal organic frameworks.
Yes, that's right.
Yeah.
So how would it change if you were to add a metal organic? How would the Nyquist plot change if you were to add a metal organic framework to on top of it?
Well, the MOFs are porous.
Yes. And maybe selective for things of different sizes.
Yeah. So I guess two ways. Let's say, for example, you have a material, right, that you're studying, and the Nyquist plot makes like one little semicircle and a diffusional tail. And then you add a metal organic framework, and it's going to increase the number one thing it might do. Let me draw out what I'm thinking.
Yeah.
These are just possibilities, and I don't know if any or all of these or how exactly it would affect the Nyquist plot with the impedance data more generally. But let's just say your Nyquist plot originally just looks like some generic kind of a thing, right? Which would be like a Randall's circuit, right? Okay. A nice Randall circuit. I should draw a leading resistor, whatever. Okay. There's my nice Randall circuit. Now I add my MOF, and let's say one thing it does is it increases the reaction rate. Well, what that means is that RCT probably goes down. So maybe one of the changes you'd see is you'd see a smaller semicircle, because RCT, which is this, RCT is the width of the semicircle. So before it was this many ohms, and now it's the red many ohms. So it's smaller. So that might be one thing that happens. Let's say another thing that it might do, because metal organic frameworks are like, porous. So let's say the microstructure now of your catalyst is porous and has some, porous structure like this. Like, I don't know. I'm sort of cartoony making it up at this point. Sometimes what this can lead to is what's called a transmission line. Okay. And so sometimes what that can look like is something like this, where you have sort of this almost like 45, it doesn't have to be necessarily 45 degrees, but you might get this sort of like lagging kind of feature, and then a semicircle. Maybe there's something else, maybe not, maybe it just goes straight down. Maybe it's like this, but this sort of, beginning of your Nyquist plot behavior might kind of do this weird kind of like, it's not a perfect semicircle. It kind of like goes up before it does something. That can be an indication of a porous electrode. That's often how it manifests. So just so as I think through this, that could be, those are the two things that come to mind. I don't have experience personally with metal organic frameworks, so some of this is a little bit of conjecture on my part, admittedly, but that it's reasonable to me that something like that could be how you would see the impedance data change.
Yeah.
So that's what I would say for that, I suppose. Okay.
As we get through this, there's a question from Dana Yedjan. I'm sorry, Mr. Hari.
Yes.
Mr. Hari. Thank you also for being a YouTube member. Can you please suggest the best high gain op amp and electrometer op amp with IC numbers for making a potentiostat circuit? I cannot. I don't think you can either. We're both.
Yeah,
we're not electrical engineers. I consulted. We both consulted with our electrical engineer about understanding how potentiostats work and operate. But I don't know enough about. I mean, there are the parameters, like when you teach operational amplifiers, we usually provide like ideal conditions. You'll oftentimes not have like an infinitely high impedance. It'll be a very large number, but it won't be infinite, or it won't have an infinite bandwidth. The bandwidth per se is also another factor to consider. How fast it responds. So there are all these things that I don't know about the picking and choosing of operational amplifiers that would go into this. But we could try to get back to you on like at least how to find them. Go to DigiKey. DigiKey is where you can buy all the electronic components you want. You'll probably find some op amps there. And I don't know. It depends what you're trying to do, but I don't know. You don't have any. You don't know an electrometer, part number, sort of say.
Oh, 5127. I have no clue.
Yeah.
Sorry, I don't. Yeah, this is not my area of expertise at all.
Yeah.
I apologize. I do not know anything about. I mean, we are electrochemists, by training, right? And we're very fortunate that we have brilliant electrical engineers that we work with who design our potentiostats and pick the parts and find the right ones to make our potentiostats work great and be accurate to a certain degree. I can speak for myself, and I'm sure you probably would say the same, that like I did not know before I got my position and have worked with our electrical engineers and our really, really bright colleagues about precisely how a potentiostat operates. Like you made a video about it on our YouTube channel. I've given a webinar on it.
Yeah.
We've lectured in workshops about it. It's definitely something that I've had to learn a lot about. And to the extent that I know, it's more about still trying to think about it from an electrochemistry point of view. Like, so I know how the potentiostat operates and how it regulates, but I don't know which electrometer from DigiKey does that process. I know what it
Yeah.
does. So if I had to, and some people, to their credit, spend their graduate school years building their own potentiostats and learning those kinds of things, and that's tremendous. And that's not something I ever really did, to be honest. So it's just beyond my knowledge base, like the electrical parts specifically about that. That's beyond my knowledge, unfortunately. So
yeah, I'm sorry.
Yeah.
All right, let's continue on getting through these questions. There's a lot of them.
From the person that asked the original questions that I
question.
answered, that the name is tricky to pronounce. But
Yes. It's asking, what's the mean of potential of zero charge and how to calculate for a certain new electrode versus a certain new electrolyte? Let's see.
I mean, potential of zero charge. That to me is always weird because it's like over what time period, right?
Well, is
this a specific thing?
I think it's the idea that so like when you put like a metal electrode or so into like an electrolyte solution, there's a natural there's a potential difference between the potential in the solution and then the potential of the electrode, and they kind of equilibrate by moving ions to the electrode surface and moving charge like electrons to or taking them away from the conductive surface. And there's a potential where the kind of the inner potential of the metal electrode is the same as the solution potential. It's when those two guys are basically equal. So one way you could do such a thing is if you adjusted the potential. Well, I'm trying to think. I would say that like when you're measuring the potential. So let me draw some of this out so you can kind of understand conceptually what I'm talking about. Let's see. Did I get disconnected again, or no? Am I still on?
No, you are good.
I'm still good. Okay, good. So just to make sure that we're all kind of clear, you have the your electrode surface. Actually, let me actually just do this. So this is and then you have your like your solution, and this is like the interface. So there is what we call the potential of the metal, M, and then there's the potential of the solution, S, right? So this is the electrostatic potential. And there's a difference. There's usually a difference between these two guys in such a way that like, okay, there's like positive charge builds up here and negative charge builds up here, so that there is a potential difference between them. This is what the double layer basically is. The double layer is just this buildup of charge on both sides because there's a difference between the potential of the solution and the potential of the metal. But we can change, we can adjust, clearly when you add more electrolyte or make the electrolyte different, you change this value. And when you use a different electrode material here, you change this value as well. Now, what you measure in a voltmeter is actually this. It's phi m minus phi s minus a tiny little IR drop minus the reference electrode potential, which is also a phi m and a phi s. So in the condition where phi m minus phi s is equal to 0, which is basically what I imagine to be the potential of zero charge, this guy kind of goes away because it's really, really tiny. So there's a part of me that thinks, oh, do you just measure negative the reference potential of your voltmeter, and like once you're at that potential, that is the potential of zero charge? That's why I think, because you have a different kind of reference electrode, you're always measuring the potential with respect to the reference. But I don't know for sure. It feels weird that like, oh, just whatever the reference electrode potential is the potential of zero charge for your system, because 0, when this whole thing is equal to 0, which is what a lot of people do, like I want to start my experiment at a potential of 0 versus the reference electrode. These guys are not necessarily they're not necessarily at a point where there's 0 charge between them. Otherwise, you wouldn't have a value 0 here. So I'm not 100% sure. There's a part of me that feels like the reference electrode potential would be, or negative the reference electrode potential would be the potential of 0 charge. But I don't know for sure. That's just my logical, like that's how I think about and would logically deduce getting that value. So maybe that makes sense. Not so sure.
Makes sense to me.
Yeah.
Sort of. I don't know.
Sort of.
Yeah, that's a tricky one. We've done that a few times. The
Yeah.
0 charge versus 0 potential. It's a little.
Yeah.
It's a little bit. It's a little tricky sometimes.
Yeah.
Underrated, unrated, and Anand. Sorry, it's probably the name. It's not. I was thinking it was another underrated sort of. Anyway,
Yeah.
just one request: can you prepare a video analyzing EIS and LSV results of anion exchange membrane alkaline electrolysis? I think I did. I think that was one of my webinars. Let me figure out which one it was, and we can link it. Let me go to our website actually, because I have it all listed out nicely. One of my webinars that I did, gosh, at this point, 2-3 years ago, maybe, was on advanced circuit fitting. And so I had people had submitted let me see here. Fuel cell, yeah, this one. Okay, PEM fuel cell. It was really an electrolyzer, I believe. But I'm finding the link right now, so just pardon a moment while I get here. So this is our YouTube channel, where it's actually where I showed the slides previously from the electrode, which, by the way, I have a follow-up on that. I think I've wrapped my head around it properly. So I was trying to figure it out how to answer earlier about electrolyzers, and I was struggling to get the right numbers, and I've got it kind of worked out. So this is why it's tough live, right? I try working things out and I feel like I got it, and then I don't have it. And so anyway, that link that I just put into the YouTube chat, that is Anand, I assume that is your name. The webinar of a 5 years ago, goodness, 2021. It's been a long time. Where I did advanced circuit fitting of a customer who had a water electrolyzer, and they did. I don't know if there was LSV, but there was definitely EIS, and I did analysis of using some Warburg short and things like that. So please check out that link. That would be a direct. And some of that analysis there. So,
all right. Chaying Chang is asking, hello, I wanted to ask what influence on potentiostatic EIS measurements results when applying different sinusoidal amplitudes while other parameters are kept the same. So what happens when you change the amplitude in a potentiostatic EIS?
Well, if your data are behaving and obeying the rules of impedance, nothing. If they're not, something. So
no, that's good.
That's technically the answer.
Technically the answer.
So one of the conditions for valid impedance, whether it's potentiostatic or galvanostatic, but you asked about PEIS specifically, so I'll just talk about potentiostatic. So one of the laws, so to speak, of impedance is linearity, and within the condition of linearity is the principle that the output is independent of the amplitude, which means that if I have 5 millivolts amplitude, and then I go to 10 millivolts amplitude, and then I go to 15 millivolts amplitude, and I have valid data, the impedance results should not change at all. Now, what may happen is they will change, and that could be one of two reasons. One is that you have made too large of an amplitude such that it is no longer linear. You could imagine if I did 400 millivolts of a sine wave up and down. That's basically like cyclic voltammetry, right? It's like I'm going up 400, down 400, up 400, down 400. That's just like CV, right? Like very fast sinusoidal CV. But if I have features in my CV and I try to do impedance over that range, well, it's clearly not linear. You know, there's a lot of things happening. It's not going to be valid impedance data. Similarly, if I have too small of an impedance and I'm barely moving up and down, I'm not perturbing the system enough at all. And so the result of having a different or larger amplitude is that I will start getting good data at all. So one of the things you can observe in your impedance data, for example, is if it's very noisy, very poor, very bad signal to noise ratio. And if your software allows you to see the raw data, which many software platforms and potentiostats do not let you see the raw sine waves. Sometimes you can see the Lissajous plots. Sometimes they don't show you even that. So it's tricky. If you have bad data, why is it bad? If you can't see the raw data, sometimes it's hard to tell. That is why, shameless plug, our company is one of the only ones that shows you the raw sine waves of impedance, the I versus T and E versus T. So you can check out for some of those things. But what you can see is that if it's really noisy and not perturbing the system enough, you need to increase the amplitude such that it starts perturbing the system. But over some range whereby your data is accurate impedance, changing the amplitude should not change the impedance data whatsoever. That is a technical condition of valid impedance.
Yes. All right, moving on. Luca is asking, is there a definite way to calculate the baseline in a voltammogram, also considering non-typical curves? Someone to calculate the baseline. Usually, it's for me, it's just eyeballing it. It's looking at a voltammogram, and then just kind of seeing how does the curve like change. There is usually a
I would say like numerically. Oh, you can finish
numerically?
your thought. I was just going to offer one suggestion.
Yeah,
like
go
quick
it.
thing. I mean, if you want to finish your thought while I'm doodling, you can.
Oh yeah, because usually whenever you have a baseline issue in the voltammogram, it's just like double layer capacitance.
Exactly.
That can also change a little bit. Maybe you have a little bit of resistance, so your voltammogram is tilted a bit, but I do not know of a way of like calculating what that baseline is. So that's the calculation thing.
Yeah. Well, like my stab at it would be like, let's say one of the reasons you want is because let's say you want the peak height, right? Like I want this, this peak height. What is this I peak current, right? And so what you really want is that, but all you have is just I is equal to however many, microamps or whatever. And so what you really want to do is subtract the baseline. And so one way to do it is just take an average of some of these points and just subtract it. So this right here is I equals 5. And this peak is I equals 20. That's supposed to be a 2. That's not a 2. I can't draw.
That's good.
It looked like a Greek letter,
Yeah.
And so I peak would be 15. Like this is like the simplest possible explanation. But like, I mean, sometimes it's like Alex said, it's like eyeball it. I don't know.
Yeah.
You're just estimating.
I'm kind of eyeballing. There's no like calculation using.
Well, okay, so the only alternative is there could be a calculation if it's like you said, if there's a tilt or something like that. Then what you can do is a more sophisticated kind of a thing. Let's say you have a lot of IR drop, and make it like really exaggerated here, but like let's say your CV is like really tilted and whatever, but you still want to get a peak height, right? And so you can hopefully see that like it's like if you drew a baseline through this, it would be like a tilted line. And so another way to do that is just take a slope between these 2 points. Take a, you get whatever this line, y equals mx plus b, and get the peak height. And what you're doing is you're just subtracting this point. I mean, this is all like algebra. I'm not going to go through the math here, but you can obviously do this pretty easily algebraically. Assuming you're in graduate school, you would have figured out this mathematics here. It's like you're finding the intercept, whatever the x here, which is voltage point is. You find the equivalent y, and you're just subtracting the peak from a sloped line instead of a flat value,
Mhm.
right? But anyway, those are the two kind of things you would do. And I'm not sure exactly what you mean by non-typical. To a certain extent, the baseline subtraction is usually what you said, right? It's
Yeah.
it's a double layer, whether it's
Mhm.
tilted or it's a flat thing. A lot of times it's very empirical. It's like you're just giving your best guess at where you think the baseline is.
Mhm.
So those are just the simple, I don't know, ways I would show.
Yeah. Srinanda asks, can you explain SHE? She kind of goes on later. I say, can you explain SHE and electrode potential? I will. So no, we have only so much time. This was from a talk I gave a while ago. But when it comes to reference electrodes, sometimes we get confused with like NHE, SHE, and RHE. The standard hydrogen electrode, so all these are based on this reaction and the potential that this reaction occurs at, which is, as we define it, usually 0. The normal hydrogen electrode is the potential of a platinum electrode in one normal acid and bubbling, or at 1 atmosphere of hydrogen gas. The standard hydrogen electrode is actually a theoretical potential of the platinum electrode where, under standard conditions, in such a way that there's no interaction with the anions from the acid. It's often the case that when you do this type of thing with an NHE, you are using sulfuric acid or hydrochloric acid, and those work really well, but there can be interactions of platinum with the anions that can affect the potential of the reaction. So the standard hydrogen electrode is that theoretical potential, assuming that there are no interactions from anions in solution. Now, so hopefully that answers the question, like, what is SHE? Now, the other question you had is, what is, can you explain electrode potential? So what I would ask you, if you're still watching, is like, how in depth of an explanation do you want? Because the electrode potential, actually, I can actually just answer this relatively quickly because I answered it earlier when I was talking about this, trying to figure out what's the potential of zero charge. The electrode potential is the difference between what's sometimes called the inner potential or the metal potential and the solution potential. So when people talk about what is just the electrode potential, it's just the difference between these two things. When you're doing an electrochemistry experiment and you are measuring the potential, what you're measuring is this. It's usually the working electrode minus the reference electrode, or that's the difference. It's the potential versus working, versus reference. Sorry. So what you're actually measuring, and then even reference, if you want to think about it, also has a phi m minus a phi s. And if the reference electrode's in the same solution as the test electrode, then the solution potentials disappear in the calculation. But oftentimes you actually have different solutions than what the reference electrode is in your electrochemical cell. But that's what the potential is. The electrode potential is the difference between this inner potential and the solution potential of at an electrode interface. If you want more, clarification, there's just a lot of questions. But if you want more clarification, like what exactly do I mean by this or this, just let us know, and I can clarify it.
Maybe you can talk about electrochemical potential.
I could talk about electrochemical potential, but but she says
it was just the same question asked many times.
But it says for a high schooler.
I guess. I suppose
it says.
I don't know if this is
for a high schooler.
I mean, could you simplify it even more? I suppose is that the idea.
So,
I don't know.
Yeah,
the subtext here.
So there's another way of thinking about electrode potential, which so there's a couple of things. There's like the electrostatic potential that's from like a big physics thing, but The way you can think about the electrostatic potentials just from the units, and as a high schooler, you may be familiar with doing some level of unit analysis. So a simple way of thinking about it, and I'm gonna again also for time and clarity, I'm not gonna go into it too much, but the units of potential. Where's my? There we go. The units of potential are volts. And volts are joules per coulomb. Joules per coulomb. I always spell this wrong. I think it's O-U-M.
Cool. It's C-O-U.
C-O-U. Yeah, see, I always switch it. I switch out where
Yeah.
C
Coulomb. I think it's C-O-U-L-O-M.
C-O-U-L-O-M. I always switch where the U is
I
supposed
think
to be.
that's right. Yeah.
I'm gonna double check it. So this is the unit of potential, which is joules per coulomb potential. Joules is energy. And then coulombs is charge. So it's a way of measuring, or a way of it. In a way, we can even use the word capacity to describe it. So something that has a higher potential means that for each charge, or the amount of charge, which can be ions, positively charged things. You can have negatively charged things like electrons. So for each charge, for a certain amount of charge, I have a higher potential if I can extract more energy from it, or it requires more energy for me to push something or pull this amount of charge. So that is a kind of conceptual way of thinking about what potential is. It's a capacity. It's how much energy per charge something has. So what does that mean in the case of this more complex thing? It just means that there's a difference between the energy per charge for charged species inside of a metal, and there's a different energy, in this case, a higher energy per charge for molecules and charged species in the solution, because it's harder to move charge in these two areas. Another way to think about it is pressure. I also like to think about pressure as a type of potential. So pressure has units, has another kind of units. Actually, it has units of joules per volume. So it also has units of force per area and stuff like this. But this is another form of potential. This is a potential that we just call pressure instead.
Don't use V for volume. Otherwise, it just looks like volts.
Yeah, that's okay.
I'm just like, oh wait, that's
it's too much volume,
yeah.
And this is pressure. It's like
it's like an acrostic.
Yeah, an acrostic. There we go.
Yeah.
Pressure. And we conceptually can understand pressure, right? If you have a tire and that tire has a certain pressure on it, it's not like the tire is let's say it's standing still, but a tire with more or less pressure means it has a higher capacity to do mechanical work, expansion work, than a tire with less pressure. And that's because it has less energy per volume. Same thing. The molecules or electrons, the charged species, has less or more energy per coulomb of charge. So that's a way you can think about it. Hopefully that simplifies it a bit. I could, of course, oh wait, just here's another follow-up.
Yeah, this was just
so electron
more
potential,
complicated answer, but yeah, basically.
Yes, yeah. So that's the answer to that is yes. It is the difference between the electrolyte potential and the metal electrode potential. Right. So that's the best way to think about the electrode potential.
Okay, so Chiaying Xiang has another question about applying constant current and voltage. So chronopotentiometry or chronoamperometry. So when I used chronopotentiometry at 0.18 milliamps, the current with 2 volts, the measurement kept running. But with CA at 2 volts, it stopped in seconds and I got 2.4 milliamps. Theoretically, I expected them to have the same effect, but they don't. Does this make sense based on your experience? So yes, it does. It's actually one of these things that does does happen actually, sort of counterintuitively to what you would expect. But when you do chronoamperometry and chronopotentiometry, they will not necessarily have exactly the same corresponding values. There's I don't know if you can explain this better than me. People do this a lot where they'll do chronoamperometry or something, and they'll get, they'll say at this voltage I applied, I got this current, but it's like at what time? Because the point is, when you apply some voltage, you get usually and you have some reaction happening. There's a decay curve because of mass transport. And the Cottrell equation is usually what describes this kind of behavior. They might mention that that after a while the current is steady at whatever value. Okay, fine. And then then they apply that current and they expect to get the same voltage they were applying previously, but that isn't necessarily what will happen. And the reality is that current, when you're applying the current, it's not behaving exactly the same way. The potentiostat is going to might end up running some other reactions, which cause the voltage to change wildly differently. Sometimes, I mean, you'd be fortunate if it doesn't go too out of whack, I suppose you'd say. But it isn't guaranteed. In other words, that it's a one-to-one kind of a thing. I don't know if you want to elaborate on that a little more.
No. I'm just thinking, when you tell the potentiostat to hold a current, its goal is to just make sure that much current is flowing, and it will vary the potential as needed, just as you said, as a function of time, such that amount of current passes.
Right.
And it does not care what the potential is. It'll just keep moving it around until your 0.18 milliamps of current pass. But when you tell the potentiostat to hold the potential at 2 volts, its goal is to just hold the potential at 2 volts. And whatever current passes, it's passing current just to maintain the 2 volts. So it's weird, but yeah, as Neil said, it's like there's a kind of a time element to it where you're optimizing for one condition, and the potentiostat's doing something just to optimize for that condition, but your electrochemical cell will react differently to optimize for that condition.
Yeah.
So
it's more about the way the potentiostat functions, I guess, which is kind of a strange phenomena. But there's also there's a time transient associated with both. That the difference between the way the potentiostat is operating, where it's letting the voltage do whatever is necessary, or measuring the resultant current. And we say that in those ways for a reason, because often controlling the current means the potential may get kind of crazy. And there's a reason why with, liquid systems, for instance, we do want to control the voltage, because if we let the voltage go wherever it's going to go, we're going to quickly destroy the electrolyte. And that could cause the voltage to then further become crazy. Whereas when you're controlling the voltage in a system where we really don't want it to go haywire, you're not in danger of ripping apart the electrolyte or the electrode because of the voltage going up to 5 volts or something weird, and that is not good from the perspective like, well, I really want to get 0.18 amps all the time because I'm trying to generate a lot of product. And it's like, the reality is you can't do that without the voltage going crazy. That's what you're learning, So that's just sort of like a thermodynamic limitation, or whatever you want to say, something of that nature. But yes, generally, to answer your question, it does make sense. So if you're seeing that, I don't believe you're doing anything wrong fundamentally. This was about the baseline, I think. Lucas says, without the Duck Mini, programs can't find the automatic. Yeah, I think that's pretty common, especially if the data is kind of all over the place, or if you have so much activity and movement and stuff that there's almost no flat section. It just goes back to our point that, like, the unfortunate answer is, like, it's up to you. Right. It's like, it's subjective. It's really, baseline is often a very subjective thing. Find a region where you think it's reasonable to say this is the baseline. If it's tough, if the automatic program isn't getting it, you're a scientist, you're allowed to make a judgment call. So you're certainly allowed to say, this is a region where I'd say that this is roughly the baseline, and then do the best that you can by subtracting it, I suppose.
Luca also has, we're going through some of the comments and stuff.
Luca
also has another question, just he is also the next one up,
Yes.
which is, can formulas and laws related with the typical situation, the duck, be applied also to non-typical situations in an experiment with cyclic voltammetry? So I would say absolutely.
Yeah, why not?
It's kind of funny. All of these, CV simulation stuff, and the quote laws and math that's governing it, absolutely apply to all kinds of situations that are non-typical and do give you these weird results. It is kind of funny, like numerically, like if you think about it, you're just getting current and voltage. And it's not like you're doing a three-dimensional model of something. It's just like, all right, the current and voltage at a certain point in time is equal to this.
Mhm.
And that's all you're trying to figure out.
Yeah.
So the answer to your question ultimately is yes, and probably it should be.
Yeah.
So that you can at least do some discussions about like what a mechanism could actually be for your reaction,
Right.
and compare it with what is similar to the non-typical results that you're getting.
Yeah. Okay,
Uh,
so let's see. I think this one's next. Biahuo has another question. If your Nyquist
No.
plot cut the x-intercept, it's easy, but if not, it's a bit tricky. Some plot perpendicular line from lowest point, some they get the linear slope. I think my approach is usually to, if the high frequency is the start of a semicircle, to do the extrapolation kind of thing. Let me draw what I mean. And I assume this is what you're sort of referring to. Is like you're trying to find the R0 or the RU, basically.
I mean, he's talking about when we were talking about that conductivity thing.
Yeah.
This is all related to that question
Right.
about
Okay. Yeah.
conductivity.
Perfect. Okay. So along those lines, or even as it relates to a, if your Nyquist plot is that, or it's just a straight line, whatever, right? Even if it's not
Mhm.
that, if it's just a straight line, but it hits the x-axis, well, then that's very easy, right? This is your z real or z magnitude, and zi, is 0. Okay, fine. If it is, I'm just drawing it out here for space, that's all. If it's more like this, and it's like there's this gap, it's like, okay, well, do I just drop this straight down, or do I extrapolate out? Now, I kind of use judgment on this, but for me, what I would probably do, even if it's a straight line, if it's like a straight line like this and there's this gap, I would probably try to fit like a CPE with a leading resistor, something like that, and I would do that. And so it's like, if I drop it straight down, I would get here. That's like option 1. And this is like option 2. And so I would go with option 2. That's what I would do, because it's like the extrapolation to get that value from which you can then get the conductivity. That's what I would probably choose to do. But as a quick option, you can just do option 1, which is basically you're just taking the Z real at the lowest ZI point. So I think that is possible. I just wanted to say that my preference probably would personally be to do some kind of an extrapolation thing in that situation.
Okay. Must Shake is back. He
Mhm.
says, thanks for answering earlier. Can you explain the difference between EIS and GEIS? That's, I guess, potentiostatic and galvanostatic EIS. What are these? What's the difference between resistance and impedance, opposition to current flow, and why is it important?
None of this is important.
I guess that is an answer. It's like in the grand scheme of things.
Yes. Why is anything important? All right. Let me show you a slide.
You're going to talk about the difference between
potentiostatic and galvanostatic.
Yeah.
It's very,
and then go into,
and I'll talk about why impedance and resistance are
and
different.
then you can answer his next question about batteries.
Oh,
he has another question about batteries.
very fun. Okay. Actually, you know what's better? It's this other webinar where I talk about this instead. This might be better. This one. All right. All right. So when you say EIS and GEIS, GEIS is a type of EIS. EIS stands for electrochemical impedance spectroscopy. GEIS stands for galvanostatic electrochemical impedance spectroscopy. And then EIS or PEIS stands for potentiostatic electrochemical impedance spectroscopy. And the only difference is what the signal in and signal out is. So in short, electrochemistry involves three variables: potential, current, and time. Everything in electrochemistry involves potential, current, and time. You are either doing something to the potential over time and measuring the current, or you're doing something to the current over time and measuring the potential. That is the only difference between PEIS and GEIS. Potentiostatic impedance is when you input a sinusoidal signal of potential and you get current output. Galvanostatic or GEIS is the exact opposite. You input a current signal and you get out a potential signal. That is the only difference. Next part of his question was what? Remind myself here. What do we have?
Oh yeah, I minimized this question
yeah.
just to make space.
Let me pull up.
His next part of his question is about what's the difference between resistance and impedance.
Okay, so
yes.
The definitionally, impedance is the resistance to a sinusoidal perturbation. Resistance is the ease or difficulty with which an electron transfers, and impedance is the ease or difficulty with which an electron transfers in the presence of a sinusoidal perturbation or input, which is what impedance is concerned with. That's why we basically call it impedance, but it has the same unit as resistance, and sometimes they are used interchangeably because they are, in some cases, like on a resistor, it's just Ohm's law. And so whether you have a sinusoidal perturbation or a DC perturbation, impedance is resistance is impedance, it's all the same. If you have something that has a phase lag, which is like every real system or a capacitor of any kind, then they are different. And the last part, why is it important? Yeah. So what's the difference between resistance and impedance and why is it important? Yeah, it's important because when you have systems, which is to say every electrochemical system, that behaves differently in its response to a sinusoidal perturbation at different frequencies, it allows us to determine a lot of information about that system simply by using a sinusoidal perturbation. So impedance's power is that it allows you to probe a lot of processes that are occurring at the same time by using a sinusoidal signal and changing the frequency with which our signal is in. That's the benefit of impedance. That's why it's important.
He then continues on to ask or say that I've made a few batteries and most of them are successfully able to charge, but not discharge. Why? My setup is electrodes radius 1.3 centimeters plus separators in a small triple electrode system, no short circuits.
I would have to know more about what you're using to know why that's the case.
Yeah.
I really don't know how I can answer without knowing the materials you're using or more specifics. I'm not even sure what you mean by triple electrode system. Do you mean anode cathode separator, or do you mean you have a reference electrode jammed in somehow?
Mm-hmm.
I mean, you almost have the antithesis of a primary battery, which is a battery that can only be discharged. You have a battery that can only be charged and not discharged. It's a bit strange. I'm not sure what would cause something like that, unless you actually are discharging it and you just flipped your leads and it is a primary battery. I'm not sure precisely what's happening. I would have to have more information. I'm not sure I really know, to be honest. That's a very curious situation, I would say, at the very least.
Yes. Mashayk's last set of questions is what are the differences between the Helmholtz layers, diffusion layer, and solid electrolyte interface?
Oh boy, Helmholtz layers are related to the electrical double layer. We usually call the inner Helmholtz plane is the electrical double layer, if I'm not mistaken, right?
Yeah, I can bring
Yeah,
up a picture if
do
you
you have
want.
the thing?
Yeah, I have a
yeah, you have the visuals for this one.
I have a
think.
visual. Yeah, so hopefully everyone can
Yeah,
see
that's better.
this. Yeah.
Let me yeah,
So
that's good.
yeah. So so at the electrical, double layer at the electrode electrolyte interface, the inner Helmholtz plane is considered the it's like if you have an irreversibly absorbed ion on the surface, it's the distance from the electrode to the center or the locus of that ion. So if I had, if this was negatively charged, it'd be a little further away, or actually it'd be closer to here, or it'd be just a little further away. The outer Helmholtz plane, OHP, is then described as the plane of closest approach. So it's just the second layer, like the next closest layer of ions towards the surface. And then you have what's known as a diffuse layer. And this is what it looks like X1 and X2 in this plot. This is from Bard and Faulkner, Electrochemical Methods, Fundamentals and Applications, the 3rd edition. Should be in the 1st and 2nd as well. But I keep drawing this potential of the metal, potential of the solution. And this is just this is what the double layer is. These are the distances and just how the potential changes across the electrode interface. The diffusion layer, there's a diffuse layer, not to be confused with the diffusion layer. And the diffusion layer is something that I don't think I have on this slide, but the diffusion layer is it's the change in the concentration profile at the electrode surface. So one way, if I get another, let me get another set of slides open, and I think I can describe it relatively easy. Let's see. I think it's practical aspects. Let's see if I have so if I now share this slide. So like when you're doing a CV and you have like diffusion, you have like an oxidized and a reduced species. And as you sweep the potential, you build up charge. Eventually, you reach a potential where you reduce species at the electrode surface. This is what the diffusion layer is. It is the change in the concentration of your oxidized and your reduced species. And as you do your experiment, that diffusion layer starts to increase over time. Truthfully, this is a concentration profile. So there is actually some of these guys here, but it's much lower than when you started, when here you had everything. It was huge, tons of stuff. But now you have less. You have less and less of these guys here. So the diffusion layer is the general it's really the change in the concentration profile of your redox species from the electrode surface. That's what the diffusion layer is.
The last thing is one of two. There's one of two answers for what the solid electrolyte interface is. The first is it's just a general term for precisely what the words are saying. It's not actually a layer. It's just it's a terminology for the place where the liquid meets the solid. It's not, it's not a Helmholtz, inner Helmholtz, outer Helmholtz plane, and the diffuse layer and the diffusion layer, as Alex just explained, are like theoretical phenomena that have explanations the way you just described them. The sometimes solid electrolyte interface is just what we refer to generally like, oh, if I have a bubble, it's gas, it breaks up the solid electrolyte interface, I get noisy data. It's just terminology for talking about where the liquid meets the solid. It's not like a microscopic theoretical kind of a term. Most of the time, that's what we mean when we say solid electrolyte interface. The other option is at a battery.
Oh yeah, that's right.
The other option,
right.
And this is a tricky thing. So whether we're saying interface or interphase. So usually when we see interface, that's what I said. It's just referring to the place where the liquid touches the metal. Sometimes people will say interface and sometimes phase, like phase, interphase. And the solid electrolyte interphase is a separate phenomena that occurs on a battery electrode, whereby part of the electrolyte is dissolved and decomposed to form a film on the electrode surface. It's not really IHP, it's not OHP, it's its own thing. It's like part of it becomes basically part of the electrode, kind of, but it's actually kind of like a diffusion layer, a fixed diffusion layer in some sense. And that's a separate situation. But the way you asked it, technically speaking, is interface. So I think it's just the first thing I said, which is it's just a term for where the solid meets the liquid.
Okay, we got a few
get
questions.
through
We'll
all
try to
these.
get through
Yeah,
that.
we'll get through everything. That's the goal.
Yeah.
And then what I think I'm going to do is I'm going to explain next week my summary of the electrolyzer fuel cell voltage thing. I kind of worked out a way to represent it a little better, but it's probably not going to have time today. So
yeah.
So Sid, who has the next question?
Yes,
Right?
Sid is the next question. Does the redox potential of the probe and the open circuit potential of the sensing system need to be the same? If no, why? What is the relationship between the redox potential of our probe molecule and open circuit potential? What is its effect? Let me sorry. Let me see. What does the redox of the probe? Okay, so that's when you say probe, you mean the probe molecule, and the open circuit potential of a sensing system need to be the same. So that answer is no. It does not have to be the same. Controlling the open circuit potential is actually kind of difficult. If no, why? So the open circuit potential. Okay, so let's draw this out a little bit, so that I kind of understand what's happening. So you've got a let's see. So you got a system. You have A plus an electron goes to B, and it has a redox potential associated. Let's just call it.
There was a follow up a little ways down. I just want to read it.
Oh yeah.
I'm asking in the context of biosensor biofuel cell, how to calculate theoretical / practical OCP OCV. No matter what, despite different redox mediators used, the OCP of my GCE, glassy carbon, I suppose, remains the same, around 0.1 volts.
Yep.
So this is related to the redox mediator thing, I believe, as well. Maybe.
Yeah. Okay. All right. So
just if that helps guide your answer.
Let's go back to this guy here, which I keep coming back to. So the open circuit potential, well, here's the thing. The open circuit potential is really this. It's so if you've been paying attention to this guy, there is the potential between your metal electrode, the inner potential of the metal, the solution, and that's the potential of the working electrode. There's the potential of the reference electrode. That's another thing. Your voltmeter measures this value, and when the current is equal to 0. So when the current is equal to 0, what is this guy? So this, let's erase this guy, and then we have this guy here. This, that's the question. That is what OCP is. So OCP is that. All right, that's the open circuit potential. When the current is equal to 0, it's the potential difference between the phi m, phi s, cares about IR, minus the reference electrode potential, which is also a phi m and a phi s. And it's the condition where the current is equal to 0. So what you've so in this whole expression, there is nothing that has to do with a redox mediator. A plus an electron goes to B. And above all, this should really make a lot of sense. If there's no current flowing in the system, then how on earth does this play a role? So here's the thing. Now, yes, I understand, like, okay, well, can't this guy affect phi m and phi s? So you're right. It can affect phi m and phi s, because now typically what happens is if you have no let's see. So I don't know enough about your redox mediators, but here is a condition, one very important condition about your redox mediator playing a role in the open circuit value, which is that the kinetics have to be fast. Kinetics has to be fast. That's like kinetics. Wrong tool. So the kinetics have to be very high. Kinetics has to be very high. In fact, the highest, the redox couple that has the highest kinetics changes and governs this phi m, basically. But it may also be changing phi s by the same amount in some ways, right? So, and phi s is something that really can't be described. But really, I don't know how much you're like changing these things, but if you add, there's something in your system where the kinetics is fast that kind of governs what this process is and moves electrons over. Also, what's the concentration, right? Because all you're talking about is my favorite Nernst equation.
There it is.
There you have it.
Took 2 hours, but it made an appearance.
It made an appearance. Because, yeah, what you're trying to do is you're trying to change the potential, and this guy is your phi m. That's your phi m minus phi s. So if you just add a redox couple and it only affects one of these guys, it might not change this at all. You need to adjust the ratio of these two guys a lot. So if you only add one of these guys to your system and you keep changing the concentration of this guy, well, this is a natural log, so it might not change it. You're going to have some Tafel relationship, right? It's like, oh, you're only in this region where you're not changing the potential very much because there's a log, unless you're adding, you have to add 10 times, right? Like 10 times the difference to see a relatively small change, like 59 millivolts of difference. So yeah, how much of the redox couple are you adding, right? These are activities, but they're also related to concentration. And there's a huge difference between those. So those are a couple things to think about. Because I know we're kind of out of time, but hopefully that's helpful in answering the question.
Do you want to go in a little longer and finish today, or
we can? I do want to answer the LinkedIn question.
Yeah,
so maybe we
sure.
just do 2 more, and then we can say we'll try to get to everyone else's question.
Sure.
I think those are the main ones. We'll get to Rupert's.
Okay, we'll get to Kanchan's question next. He's been waiting patiently. I know there's a lot of questions, and we're getting swamped today, and these things happen. But Kanchan had asked, apart from charge transfer resistance, RCT, and electron-hole recombination, what other information can be extracted from the semicircle region in an EIS Nyquist plot? One of the main things is a time constant, actually. So there is a way mathematically to get the capacitance value from a Nyquist plot, but more often, the semicircle region in a Nyquist plot, you do a circuit fit and you get the R and the C values, right? Well, the charge transfer resistance, which is the width of that semicircle, is associated with a charge transfer process, and that process has a certain speed associated with it, which is related to its kinetics. And the multiplicative of R times C is called a time constant, tau. And it is, roughly speaking, the amount of time for 60% of the capacitor to be charged up. So it's there's estimates where people say 5x that is the speed. That's roughly the speed. You can just say, generally speaking, like if I have a RCT and I have a capacitor, that's the semicircle, but it's an R and a C. I multiply R times C and I get some amount of time. Usually, maybe it's microseconds, something in that range. That is what's called a time constant. And that's basically, relatively speaking, the speed associated with that charge transfer process. So that's one of the main, all other kinds of diagnostics quantitatively. that we can get from the semicircle region in a Nyquist plot. I think that's probably the most direct thing I can think of. There might be other maybe tangential kinds of things, but that's the most obvious one for me that comes into mind. And then Nikhil, I guess, will answer that one.
Yeah,
Is that
I think
so?
that'll be the last.
So I have a question regarding anodic and cathodic peaks of a material observed in cyclic voltammetry. Are these peak positions expected to remain constant, or they typically fall within a range?
So it's interesting.
Depends.
Yeah, it's like theoretically they shouldn't change.
Right.
But there's often times in different chemical systems. So a lot of things can happen. As you cycle, you may get things like increased IR drop, so to say, like or basically some junk gets on your electrode surface, and like the peak splitting starts to increase because of solution resistance. Basically, you have a resistive element in your system. And theoretically, the positions of the anodic and the cathodic peak should remain the same if it's like perfectly reversible, does not contain an IR contribution, and also doesn't deviate from like a chemical reaction or has a pH dependence. In that case, yes, they should be in the same position. But if there's drift in your reference electrode, that's another thing that can cause problems. So this is one of those theory guides, experiment decides.
Yeah, it all comes back to ask us anything about what experiment decides.
Yeah.
So that's been the theme of today's episode. We're going to have to call it. We're a little over time here. We do appreciate everybody. Rupert, we see your questions. What we've done is saved them.
Yes.
And so apologies that we just were very inundated today. We appreciate it, and we hope we've done our best. I do apologize. We didn't necessarily get to everybody. It does happen. Next week, we will try to answer your questions, Rupert, about OER and copper oxide nanoparticles. As well, I'm going to clarify next week fuel cell versus electrolyzer. I gave it some thought while Alex was talking about something, and I was absolutely not listening. And I apologize in the middle there. I felt scattered. I had some things mixed up. It's just a bunch of negative signs between a fuel cell and electrolyzer. And I had some details kind of backwards. So I'm going to clarify that for my own pride and consistency next week. I think I can illustrate it pretty well, but that will have to wait until next week. So until then, again, thank you everybody. We appreciate, as always, the engagement, the questions. We hope everybody has a good weekend, good week, and we'll see you next week. Take care.